Heavy water. Most people have heard the term. Almost nobody can explain what it actually is. In our last episode, we documented America's $2.7 billion bet on uranium enrichment and the natural uranium reactor path that uses heavy water instead. That episode raised a question I suspect many of you had. What exactly is heavy water? It is not radioactive. It is not glowing green. In small amounts, including the trace amounts already present in the water you drink. It is not dangerous at all, but it is not ordinary water either, and the differences, subtle as they are, have shaped nuclear physics, wartime strategy, and energy policy for nearly a century. Tonight, on Words with Wentz, we are going to explain it properly, what heavy water is, how it is made, where it is used, and what it does to the human body in amounts beyond the trace. Ordinary water is H2O, two hydrogen atoms bonded to one oxygen atom. Most hydrogen atoms consist of a single proton, nothing else in the nucleus, but hydrogen has a heavier cousin, deuterium. Deuterium has one proton and one neutron in its nucleus. It is still hydrogen. It behaves chemically like hydrogen in almost every way, but it is roughly twice as heavy. When both hydrogen atoms in a water molecule are replaced by deuterium, you get D2O, deuterium oxide, heavy water. It looks identical to ordinary water, colorless, odorless, tasteless at low concentrations, but it is about 10% heavier. It freezes at 3.82 degrees Celsius instead of 0. It boils at 101.42 degrees instead of 100. Those tiny differences, in weight, in the way its molecules move and react, are what make it useful for nuclear reactors, and what make it a hazard in large enough concentrations in the human body. Heavy water was discovered almost by accident. In 1931, an American chemist named Harold Urey was working at Columbia University when he identified a heavier form of hydrogen in a sample of ordinary water. He called it deuterium. 3 years later, in 1934, he was awarded the Nobel Prize in Chemistry for that discovery. What Urey had found was that ordinary water contains trace amounts of heavy water naturally, roughly 1 part in every 3,200 to 6,400 molecules of ordinary water is actually D2O. It is always there. You have been drinking it your entire life, in quantities too small to matter. But the discovery opened an entirely new field. Within a decade, nuclear physicists understood that heavy water could slow neutrons in a way that made a nuclear chain reaction possible without enriching the uranium first. That realization made heavy water strategically critical and made Urey's discovery one of the most consequential in the history of modern science. Producing heavy water in commercial quantities is one of the most expensive and energy-intensive processes in the nuclear industry. The primary industrial method is called the Girdler sulfide process, developed by Atomic Energy of Canada Limited and patented in 1959. It works by cycling ordinary water against hydrogen sulfide gas at alternating temperatures, exploiting the fact that deuterium migrates preferentially between the two substances at different temperature ranges. The process is slow. It takes enormous volumes of water to concentrate enough deuterium to produce useful quantities of heavy water. To produce a single kilogram of heavy water, you must process thousands of kilograms of ordinary water. Canada became the world's dominant producer of heavy water for exactly this reason. The country built large-scale production facilities specifically to fuel its CANDU reactor program. The Bruce Heavy Water Plant in Ontario was the largest heavy water production facility ever built, capable of producing hundreds of metric tons per year. The United States operated heavy water production facilities during the Manhattan Project and the Cold War, including at the Savannah River site in South Carolina. Most of those facilities have since been decommissioned. Heavy water has 4 primary uses today. First and most significant, nuclear reactors. In CANDU-style heavy water reactors, heavy water serves 2 functions simultaneously, as the neutron moderator that slows neutrons to sustain the chain reaction, and as the coolant that removes heat from the reactor core. This dual role is what allows CANDU reactors to operate on unenriched natural uranium. Second, medical isotope production. Heavy water reactors are among the most efficient producers of medical isotopes, including molybdenum-99, which decays into technetium-99m, the most widely used radioactive tracer in nuclear medicine worldwide. Third, scientific research. Heavy water is used in chemistry and biology laboratories as a tracer because its slightly different weight allows scientists to track where molecules go in chemical reactions and biological processes. Fourth, NMR spectroscopy. Nuclear magnetic resonance instruments, the technology behind MRI scanners, use heavy water as a solvent in laboratory analysis because it does not interfere with the hydrogen signals the instrument is trying to detect. This is where heavy water gets interesting and a little surprising. First, the reassuring part. The trace amounts of heavy water naturally present in ordinary water, about 1 part in every few thousand molecules, are completely harmless. Your body processes them without any issue. You have been ingesting them since birth. At moderate concentrations, if a significant fraction of your body's water were replaced by heavy water, the effects begin to show. Heavy water disrupts cellular processes because deuterium bonds slightly differently than ordinary hydrogen. It slows down enzymatic reactions. It can interfere with cell division, mitosis, and at full concentration, pure heavy water. A 2025 study published in PLOS. Water found something unexpected. 100% heavy water triggers apoptosis, programmed cell death, in human cells more potently than exposure to high-dose ionizing radiation, more potently, not less. The mechanism is not radiation. Deuterium is not radioactive. The damage comes from the kinetic isotope effect. Chemical reactions in the cell run at the wrong speed when deuterium replaces ordinary hydrogen. DNA repair processes are inhibited. Cells die. The same study found that diluting heavy water approximately 10-fold with ordinary water completely abolished the toxic effect. Dose is everything. Context is everything. Heavy water in a nuclear reactor coolant loop is not the same as heavy water in your bloodstream. Now you know what heavy water is. A form of water where the hydrogen atoms are replaced by a heavier cousin called deuterium. Harmless in trace amounts, disruptive to cells in large concentrations, and the source of tritium contamination in heavy water reactor systems, a monitored and regulated risk. In our previous episode, we documented America's $2.7 billion bet on uranium enrichment, a choice to process natural uranium into a more concentrated fuel rather than use it directly in heavy water reactors. That choice has trade-offs. Enrichment requires complex, expensive infrastructure and produces a fuel cycle dependent on centrifuge technology. Heavy water reactors require expensive heavy water production and generate more tritium as a byproduct, a regulated radioactive contaminant that does not arise in the same way from light water-enriched uranium reactors. Neither path is without cost, neither is without risk, and neither is simple. What both paths share is a starting point, uranium in the ground, mined from places like the Black Hills of South Dakota, leaving behind the tailings this series has documented. The documents are in the description. This is Words with Wentz. Know the truth.
Let the signal cut through the noise. Reading between the lines. Every story leaves a trace, unlocking time and space, finding truth